Yeah, there you go. Dan, you're next on the list. Dan, Ray, and Rick Hambley were down in a week ago today, down in Haswell, and Dan finally got to do some actual radio astronomy work. And down at the bottom of this first slide, you can see the other folks involved that are not on tonight. But there are technicians: Glenn Davis, Lewis Putman, and Phil Gage. They're the folks who keep that the tracking system up and running, and of course Ray, who does the feed horn work. So go ahead, Dan.
All right. Yeah, this is something I don't know how exciting it would be to do a GoPro or film this, because believe me, there's a lot of fumbling around. We're trying to tune up an SDR for the first time of something we've done, and we spend a couple of hours just tuning things up and testing, looking at spectrums and testing things before we finally get going. But anyway, yeah, so Rick, Ray, and myself were down at Haswell last Monday. We wanted to try first time for maser, and we also spent a couple hours on pulsars. We tried to get a new pulsar. We were not successful. It just, at 1400, they're too faint. So anyway, this is a maser. Let's see. I think it was last Tuesday after I got home. I went through a couple of files and saw that we'd gotten a good detection, and I put together a little file and sent that out and put it on the groups IO. But then yesterday I went back and looked at the rest of the files, and I found a much better one, because we'd taken several collections. So I found a better one. So what I'm showing here in this plot is better than the one I sent out last week. And Bill Thomas has posted this presentation on the website if you are interested in that. So this was our very first maser detection, and I'll go over what a maser is in a minute. But we were pointed towards Cassiopeia. In the Perseus arm, there's a star-forming region. So it's a ionized hydrogen star-forming region called W3, and it's about 6,000 light years away. And it's known to have a number of masers there, hydroxyl masers. The rest frequency is 1665.4 megahertz. That means that's the frequency of emission. Of course, we're going to detect it differently because of Doppler effects. So we're either going to detect it shifted up or down, depending on the Doppler. I used an SDR play at 5 megahertz bandwidth. The sample rate, I used a half a second. Next time, I'm going to put that down to maybe a 100th of a second. I want a much higher resolution so I can get more detail. And 10-minute collection seems to work on this one anyway. So the feed, we have a 1420 megahertz feed horn. So the feed horn is tuned for 21 centimeters. It has a antenna probe inside for 21 centimeters and a RF chain for that. And so what Ray did was he modified that because 1600 megahertz is 18 centimeters. So there's not a whole lot of difference between 21 and 18 centimeters. So some of these 18 centimeter radio photons, these waveforms, are going to be bouncing around in there. And so Ray stuck in a little bit shorter probe, a second probe, and a second RF chain with LNA and filters for the 1600 megahertz. And so that's what we successfully used for the first time. Ray, did you want to say anything about it? Because you're the one that implemented it and built it.
Oh, I might say that I didn't actually shorten the feed probe at all. It turns out when I measured the 1420, it worked as good at 1665 as it did down at 1420. So I simply built a couple of preamps. I cascaded them, and we went for that. And after I got my cable issue squared away, why we detected the pulse very well, or the frequency. But it was actually the same exact feed probe that we used on 1420.
Okay, yeah, that's fascinating that it works out well. Yeah, we had a very strong signal coming down on 1600. And so I appreciate Ray's work on the hardware and the RF chain, and then But yeah, so we want to acknowledge the System 1 guys, Phil Gage, Lewis Putnam, and Glenn Davis. Not only do they maintain the System 1 and keep the pointing and tracking working accurately, last year I sent them a list of 35 masers with the right ascension and declination and all the information. So they added all those masers into the database list. So anytime anybody wants to go down and try a maser, there's 35 of the brighter ones already in the table, easy to look up and start working. So what is a maser? Basically, a circumstellar hydroxyl maser. Hydroxyl is OH, it's a molecule. The circumstellar maser is a shell of gas. It's a shell of expanding gas around a red giant star. And inside this shell, there's molecular hydroxyl. And this comes from ultraviolet radiation on H2O molecules in that shell. Then strong infrared radiation from the red giant star excites OH to maser transitions at 1612, 1665, 67, and 1720 megahertz. So there's 4 different emission lines there from this hydroxyl molecule. These are atomic transitions, very much like a laser. You have a pocket laser. A laser is doing these atomic transitions at specified optical frequencies. Maser is doing similar atomic transition at certain microwave frequencies. And that's what we're detecting. So these are emission lines. They often show a double peak. This diagram here from Wolfgang is very helpful. And it shows, as we're looking at the line of sight towards this red giant star with this expanding shell, we're going to see the near side and far side maser, and they may each one be shifted a little bit differently because they're going in a different direction. And so we'll do the VLSR correction for that Doppler shift. Masers can be very bright. They're highly variable, but they can be quite bright, and they're very large. These are very large shells, 1,000 AU or larger. Now, all of that is sounds nice, but that's not what we were looking at last Monday. So down here in italics, I put the little disclaimer that masers also are present in H2 star forming regions. So W3 is not one of these circumstellar masers. W3 is H2. H2 is ionized hydrogen. It's a star forming region. So there's a lot of gas and dust and stars forming, a very dynamic, chaotic, hot environment. But it's the same atomic process in terms of the hydroxyl molecules being excited by that infrared radiation. So we were actually looking at a star forming region. And this is the plot that I had. This is the best one I could find. So on the left is just the raw average spectrum. So there's a little bump there at 1665.7. And then on the right is what we call the calibrated spectrum with the VLSR. That's the local standard reference frame. That's the Doppler shift adjustment. Calibrated means we subtract a cold sky from the hot sky, from the source. So I list the file names there. I use a date timestamp, UTC, or actually this was local time. And then there's a subtraction performed to raise up any signal out of the noise. And so what that means is what we were doing as we was fumbling around Monday morning is we would point first, we would use System 1 to go to the source, that target right ascension declination. And then using Stellarium, I'd found a cold spot just a few degrees away. Cold spot means there's no maser emission in the beam at that look angle. So we would do a 10-minute collection for cold at that frequency and at that gain, and then shift back to the target and do the same collection, 10 minutes at that gain. And we did that several times, and each time I had to keep reducing the gain because I just had the gain up too high. So it took several iterations to kind of dial it in to get something like what you see here. But the system 1 worked fine, and we had a great signal coming down. This is the raw results. The software I'm using is it's on GitHub. Anybody can get it. It's called Astro Virgo. I've modified it just a little bit, and but it does the VLSR correction. It's a hydrogen package, but I'm obviously using it up here at 1600 instead of at 1420. So that red dashed line is the rest frequency of 1665.4. On the left, you can see a little bit of a spike right at the center. That's the DC spike. When we were testing there on Monday, using the signal generator and a discone antenna, we injected a signal. We just broadcast a little signal, dish picks it up, and so we had a big spike in the middle. But when we turn that off, we notice there's still a persistent DC spike at right exactly at center, 1666.0. So that's the bigger spike in the middle. The smaller spike is the actual hydroxyl signal there on the left. On the right is the waterfall, and even though this was my best plot of the day, you can see I'm still partly saturated. I still had the gain up too high. So next time I'll turn the gain down more and bring that signal out a little bit more. So how do I actually know that I got that? So I have some verification tools. On the left, I use the Sarah account. I'll log in remotely to the Greenbank 20 meter, and I ran a 2-minute collection on several masers, and this is what W3 looks like at 1665 and 1667. So there's peaks there at 1665.7 and also at 1667.7. It's a much smaller peak. So that way I get an idea what it should look like. The Greenbank, there's a red trace and a green trace because they have 2 simultaneous receivers. One of them's XX and the other one's YY, so different polarizations. Oh, by the way, when we were down there last Monday, we started at 1612. We tried several iterations at 1612, didn't get anything, so then we moved up to 1665. And that's where we finally started getting a signal. On the right of this plot is Wolfgang's plot. So this is from Germany after Pelier Stockert. They have a 25 meter dish, very good electronics on it, very good computers. And this is zoomed in, and it shows that the velocity is a negative roughly 45 kilometers per second. Negative means it's blue shifted. It means it's approaching us, coming towards us. And I got roughly the same, roughly about minus 45 kilometers per second on the velocity. And then the Hawk RAO stands for, so there's a amateur radio astronomer in Australia, and it's near a village or something called Hawk. And so it stands for Hawk Radio Astronomy Observatory. The VLSR calculator, he's had out there for years and it got out of date. This guy, this amateur in France, F4KLO, updated it and put it on this website. It's very handy if you're doing hydrogen or masers or anything like that for emission lines, because it'll calculate the radial velocity that you should see from Haswell for whatever direction you're pointing. So it's based on the time and location. And it also determines what frequency you will see a spectral line at, whether it's hydrogen or some maser emission. So I use that to verify that we got the right frequency and the right shape. So after moonbound season, hopefully in December, we'll put this 1420 feet back up and try masers again. The first one is the star forming region. All the rest, W49 and the rest of them, are all actually circumstellar red giant shells that I was talking about earlier. So those 5 masers will be up. Some of them in the day, some of them at night, some circumpolar. But any of those we should be able to detect and work on those at the various frequencies. So any questions on the maser detection? I do
Uh,
have, yeah,
Actually, could I ask a kind of a stupid question here, since I'm kind of new at this? Your peak was at about 165.7,
yeah.
and you were saying that you're expecting it at 165.4.
No, no, 0.4 is the rest frequency. That's what it's emitted at the star. But there's the Doppler effect. The star's moving and we're moving around the Earth is moving around the sun. So
Yes.
all the Doppler effects will shift the wavelength, either make it shorter or longer, shift the frequency.
Correct. What I was wondering, so it's obviously moving toward us in your sampling here. Does the movement of the Earth toward it account for all of that, or is that a much higher velocity? I don't have a feel for how much shift versus velocity.
So yeah, the Earth, its own rotation on its axis, so it depends on the time of day where we are and where we're pointing into the sky. But the Earth motion around the sun is a major factor, and then the star itself, the red giant, is moving. In this case, I don't know if it's how fast it's moving. So I think the Earth rotation is the bigger factor. There's two. So this is called topocentric. Topocentric means what frequency you should see it at your location. You can also do barycentric. Barycentric means the solar system center of mass. So it's at the sun.
Mhm.
So that way, if everybody converts to barycentric, everybody would have the same. But everybody uses topocentric, so it's going to be a little bit different depending on where and when you observe.
Yeah, I think you've answered my question, but I was just wondering, that shift, is it explained fully by the Earth's motion, or is that star formation area moving toward us at a high velocity? Again, I just don't know what velocity this point, what was it, 0.3, wait, it was 0.5, so 0.2. Oh no, it was 165.4, so it'd be a 0.3 shift.
Yeah.
Do you have a velocity number for that by any chance, approximately?
Of the maser is minus 45 kilometers per second. That's the radial velocity.
Well, that would shift it down though, right?
Yeah.
But we see a shift up, so I'm just wondering if there's if you have an
No,
approximation of the velocity that's approaching us.
So the frequency goes up as the wavelength goes down.
Oh, sorry. Yeah, you said wavelength. Okay. All right. I think I've embarrassed myself enough.
No, that's a great question. And so the program I'm using here, Virgo, it actually has GNU Radio in it. So GNU Radio does the data collection, and then it has Python code to do the calculations. And then there's a library called AstroPy. AstroPy is a well-known astronomical library that does all the coordinate conversions, and it also does the VLSR calculation because it's somewhat complicated. I wouldn't want to have to write it up again, but so it's kind of a standard library, the AstroPy, that does that calculation. Nonetheless, this was my very first test case, and I wanted to make sure that I was doing everything right. And so that's why I use this calculator here at the bottom, the Hawk RAO calculator, because it steps you through. You just enter in the values on the website, and then it will tell you the contributions there.